Okay, so we left it in class last time as at the point where we've completed the computation of how the observer Markov parameters can be extracted from the data, and how once we have the observer Markov parameters, we can write a little code that will then unzip the observer Markovs into the Markov parameters. In order to take the thread at that point, let me just put the last thing that I did in class, which was to illustrate that by looking at the recurrence, the first Markov parameter actually proved to be the first observer Markov parameter part 1 plus the first observer Markov parameter part 2 multiplied by the 0 Markov parameter, which we can call either observer or not observer, because in both cases it's just simply D. It's the same, right? Now, you can go through the motions and try to derive this if you'd like. There is no need. It's kind of a tedious process, but once you go through that tedious process, you conclude that the Markov parameter K can be obtained from a recurrence in which you take the observer Markov parameter K part 1, you add the observer Markov parameter K part 2 multiplied times the 0, just like we had here, sort of. But you also have this summation here, which is from J equals 1 to K minus 1 of the previous Markov parameters Yj times the previous observer Markov parameters K minus J part 2. Okay? That is the sequence that one has to program. Now, because there are only a certain number of non-zero observer Markov parameters, it's obvious that when you code this, or it's obvious that this expression for values of K which exceed the non-zero Markov parameters, only the summation term remains. Because let's say if there were 10 non-zero observer Markovs and you're calculating the 20th Markov parameter, then that is, this part is 0, since these terms would be 0. And you would only have this summation here. Okay? So those are your Markov parameters. And we illustrated in class a little quickly program in which we did it and from the few observer Markov parameters extracted the Markovs. In the situation where there is no noise and we have perfect input and output data, then it is possible to obtain a set of observer Markov parameters which are not an approximation when we say that the others are 0, is that the others are 0, okay? Because there is an exact mapping, an ARX mapping between the prior outputs and inputs for some time and the current output. Okay? Now, what we have at this point then is methodology that allows us to extract from input-output data as many Markov parameters as we want. Now, we know that the Markov parameters are given by the product. The Markov parameter K is given by the product CD, we could write it as C or CD, but times AD K to the minus 1 times BD. Our objective is to untangle these matrices A, B, C. We already know D because the observer Markov parameter 0 is D, right? So now what we wish to do is to untangle A, B, C from the available Markov parameters. And to do that, we begin And I'm going to erase this to have as much room as possible. We begin by defining, let me see, wait. Maybe I can do this all in one chunk without erasing. We will begin by defining a Hankel matrix K as an ordering of the Markov parameters. So imagine that we start with Markov parameter k plus 1. So if we form the matrix H10, we begin with 11 over here, right? And this matrix goes like this. We put the following Markov next to it and so on. And we stop at some point, which is for us to decide, which is the k plus alpha. So we begin at the k plus 1 and stop at the k plus alpha, right? Now, in this direction, we go by increasing order also to k plus 2. This one would be the k plus 3, etc., like that. This one is the k plus 3, and so on, until the Markov parameter k plus beta. Excuse me. So again, beta is for us to decide at this point open. In this direction, this last Markov here is the Markov k plus alpha. And you can see that in order to go from here to here, we had to add beta and subtract 1. So that's k plus alpha plus beta minus 1, right? So this is the Hankel matrix HK. It is simply a definition, right? It is simply a definition. How many Markov parameters do we need in order to form that matrix? Obviously depends on our selection of alpha and beta, and we will see, but obviously it's this is the biggest index, right? So to form, let's say, H1, the one with the minus 1 cancel, we need alpha plus beta Markov parameters. Okay, now we recall at this point that the observability block, which I am using the notation in the notes, in the type notes that have been posted, because I can't remember necessarily exactly what I do in previous classes, but this is consistent with the type notes. So if we take the observability block, you will remember that the observability block is given by the matrix CD, CD, AD, CD, AD squared, etc. And that the last one, if we call this one CD, AD to the alpha, did I use alpha here? Yes. If we call this CD, AD alpha to the minus 1, we would call this the observability block alpha. Okay? Now, you may also recall that we defined the controllability block somewhere along the line, and as Q, and the controllability block begins with BD, and then it has what? AD times BD, AD times BD squared, and it goes on, and the last one that we put in there is AD, let's say, to the beta minus 1 BD. Then this would be the controllability block of size beta. Okay? Now let me check how the thing looks. Okay, I haven't exceeded anything, so it looks fine. Now, what we want to show now is, I have some room down here. It's not a lot of room, but it should be sufficient. if we take P alpha, okay, the observability block, and we multiplied P alpha times AD to the K, and then we multiply it by Q beta, let's try to see what that gives us. That gives us, first we have here P alpha, which begins with CD, CD, AD, etc., right? Then we have AD to the K here in the middle, which will add AD to the K of all of that. And then we have over here the controllability block Q beta, which is right there, BD, AD, BD, etc. Now you can see, if you track that multiplication, let's see what that multiplication gives us for the first entry. For the first entry, the 1, 1, we would get CD, AD to the K, BD, right? CD, AD to the K, BD. Now that entry right there, that entry is this, right? That's Markov parameter K plus 1. If we look at what is the second value here, we would have CD AD to the K plus 1 times BD, right? So here goes CD AD to the K plus 1 times BD. And you can see that that is Markov parameter K plus 2. So that this entry is this, okay? You can continue that process and you will conclude, as you do the whole thing, that this product is exactly this matrix. That is, the observability block of size alpha times AD to the K times the controllability block of size beta is the Hankel matrix HK. Okay? That is the Hankel matrix HK. Now I don't have enough room on this board to continue writing, so I'm going to have to erase, but I'm going to erase everything and begin right here again with HK is equal to this part here. Okay, so we have that the Hankel matrix is equal to these things. Now, let's keep in mind that we do have HK if we like, for any K that we want, right? I mean, provided we've calculated enough Markov parameters, we can form any Hankel that we'd like of any K for any alpha and any beta within limits, right? Within the limits of the Markovs that we've extracted. So let's take a look at the case of H0. Let's say we take K equal to 0. Then H0 is P alpha, AD to the 0 is the identity, times Q beta, right? And H0 is the Hankel matrix that begins with H0 is the Hankel matrix that begins here with the first Markov parameter that is not D, right? Because the H began with HK plus 1, right? So H0 begins with Y1 and then Y2 and then Y2 is here. And again, you notice these matrices are Hankel because it's the anti-diagonals that are equal to each other. Of course, not Hankel, but block Hankel, right? Because these y's are not numbers, they are matrices. Okay? So we can form H0, and then we can see that H0 is for some alpha and some beta, right? And we see that H0 can be taken to be the product of the observability block of size alpha and the controllability block of size beta. Now, assume that you perform a singular value decomposition of the matrix H0. And to use the notation that I've used in the notes, we would say that we can write H0 in a singular value decomposition as R. I normally use U or something, but I guess this is the way I did it, times sigma, which I normally use S, times S transpose. So this is a singular value decomposition of H0. Now, the next thing that we see is the following. The observability block, right? The observability block is a matrix that has P alpha, right? It's a matrix like this, C, CA, CA squared, etc., right? So the rank of the observability block is n, because this is the system order, right? Or at least the order of what is observable, because there could be something non-observable, but let's say that's the order of the observable system is what we have as P alpha, right? And let's assume for the time being that everything is observable, so that's the rank of the system. Now, the Q beta is like this, right? And that is BD, AD, BD, etc. And the rank of this Q beta is also equal to n, right? This is n. Or at least it is the rank of what? Of the controllable part of the system. Okay? Now, if I wanted to get rigorous, we could distinguish these two things and just call n observable, n controllable. And then we could argue one thing. We could say, however, the rank of a product of matrices is never larger than the smallest rank, right? And since H0 is the product of P alpha and Q beta, the rank of H0 is no larger than the smallest rank of these two things. Therefore, we will find that the rank of H0 is the smallest or of the observable or controllable parts of the space. Now, when the thing is observable and controllable, both of these things are equal, and they are equal to the order of the real system n. Let's, for this discussion, assume that that is so and not make the distinction. Therefore, the rank of H0 is the system order. Therefore, notice the following point. When we start this process, we only have data. We don't know, or at least we take the position, because we are in identification, we take the position that we don't know where this data is coming from. In fact, we may know, but we take the position that we don't know. So, we do know one thing, because it's necessary for doing what we are doing so far. We assume that the data is coming from some system that it's linear and it's finite dimensional, because that's how we started our derivations. Now, on the premise that the system is linear and finite dimensional, we were able to deconvolve the observer Markov parameters from the data and to extract the Markov parameters from the observer Markov parameters. Next, using the Markov parameters, we have formed a Hankel matrix of, we've called H0, and we now can find, by simply looking at what is the rank of H0, we can find out what is the order of the system that generated that data. Okay? So at this point, we find whether the system was 5 degrees of freedom or 10 degrees of freedom or what, because the rank of H0 is the order. Okay? Now, when we go later on to the case where there is noise, there will be not perfect rank, but decreasing singular values and so on. But that means then that if look at these products here, we can see that H0 is R, and R is going to be like this. Then there is going to be sigma, which is of the same size as the matrix, and then there is going to be S transpose, which is of the size of the rows, right? So let's see. This matrix is this is H0. How many rows are there here? We said there were alpha, and this one of these guys has M output, so this is alpha M rows, right? And how many columns are there here? Beta times R, right? Because each one of these guys has R inputs. Remember, these are not observer Markovs, these are the Markovs themselves. So we have alpha times M rows, beta times R columns. Therefore, the first matrix on the singular value decomposition is an alpha times M by alpha times M matrix. This one is an alpha, a beta times R matrix, and this is an alpha by M. And this matrix here is a beta times R multiplied by a beta times R matrix, right? Now, the matrix sigma, which are the singular values, we've already shown it's going to have to be of this form, sigma n and zeros, because that matrix is diagonal, right? And since there are only n non-zero singular values, assuming that we've chosen alpha and beta large enough, it will look like that, right? We can then convince ourselves by the rules of matrix multiplication that of